Wow, we're at the last section, 10.6, and we're going to apply everything we've learned. Even though we did learn most of this during the chapter, we're adding that growth and decay reference value. We used it only as a given concept, but now we're going to review it. So here we go. Exponential growth and decay function defined by our textbook as let y sub o be the amount of or number of some quantity present at time equals 0. So it's the beginning. It is the beginning value. And when t is at the start of when we start making this growth equation or decay equation happen. The quantity said to grow or decay exponentially if for some non-zero constant k, the amount present at time t is given by y sub o, y sub o times e, the natural number, and the amount present at t time. So k is a constant, and that is the rate of that decay. It is some kind of a percent value or a value period. If the substance decays according to the equation y equal y sub o to k of t, then where a equals e of k, the substance that causes k to be positive or negative, or if k is positive when the increase in time leads to an increase in quantity, or k is negative when, typo, an increase in time leads to the decrease in quantity. So if we have a negative k, it is a decrease. If we have a positive k, it is an increase. So here we have our first exposure to it. And I want to see. All right. So the exponential decay equation of y equals y sub o e of k of t when k is less than 0, where y sub o is the amount of substance present at the time t equals 0, and y is the amount present at the time of t. Using the definition of half-life, okay, at t, capital T, y equals 1/2 y sub o. So the equation be represented as 1/2 equals e to the kt. Taking the natural log on each side, we write it as a natural property of logarithms. All right, so I got this out of the textbook, and hopefully you can see where e to the kt, capital T, comes in about in the equation. All right, now let's get to some problems. All right. If the half-life of a radioactive element, which decays according to the function a of t equals a sub 0 e to the negative 199 10,000ths t, where t is a time in years. All right, so we want the half-life. So we're assuming that a at the start is 1, and a of t is 1/2. So this is how we're going to solve this problem. So I'm going to have the equation 1/2 equals 1 e to the 0.0199 t. All right. So now that I have that, I'm going to do the natural log on both sides. ln of 1/2 equals ln of e to the negative 0.0199 t. Well, these are inverses of each other. So now I have ln of 1/2 equals negative 99t. Well, now all I have to do is divide by the negative. So 1/2 divided by the negative 0.099 will give me t. So now we stick this in the calculator. That. And we're going to state natural log of the 0.5, close parenthesis, divide, make sure we close the parentheses, negative 0.0199. All right, so I have it correct, and I enter, and I get 34 and 8/10 years. Take for this item to go to half of whatever it started with. So this is our first understanding how it works. All right, so now let's look at this next equation. In your homework, you're not going to have a litany of questions. I just want a small exposure should you go into more science where decay is important. So the amount of carbon-14, that's the most famous, presents after t years is given by the exponential equation A of t equals A sub O, with k equal to negative ln2 divided by 5,600. Use the carbon-14 dating of charcoal found among the fossilized leaf fragments. Botanists arrived at the age 47,000 years for a plant. What percent of the original carbon-14 in the charcoal was present? All right. So in this case, we're going to look at what we have. Here we go. So it said A of t equals A of O t. All right. Now what was given? That K was this part right here. And we were given that T was 47,000, right? Yeah. And so all we need is what it was to begin with. Right. So let's see what we can do. T was the age, 47,000. Our A, do we know our A? It is 1. I'm going to put it as 1, start. The up caret, I'm going to make it kind of big so we can know what we're talking about. Negative ln of 2 divided by 5,600 times the 47,000. Right. Now all we have to do is figure out what A of t is. So we're going to do second ln, and we're going to enter negative ln of 2 divided by 5612 times 47. Right. Okay, because that's all we entered, and we get ugly number right here. So we're going to round to 4. So the asymptote that we had was 3 thousandths. of the amount. So that would be our answer. So now we're going into evaluating true rate of interest earned. Right. And what I want to do here for compounding. All right. So what this does is that compounding adds interest in and makes a new percent. So we want to look at how this works first. All right. So let's talk about simple interest. Simple interest is calculated by the formula A, future value, equals principal times 1 plus RT. All right. And this is how we would do it. So we're going to do a test only on simple interest. I mean, it's not compounding, just simple interest. And we want to do it for 2 years and see what happens. Okay. So if let the P equal 100 and the rate equal 5%, and it's annual. Okay. So A equals 100, parenthesis 1 plus 0.05, and we're doing it times 1. So I would have on my calculator 100, parenthesis 1.05, close parenthesis and enter, and I would have $5 made. So on the second year, I'd still have 100, 1 plus 0.05 for 2 years, and that would give me 100, parenthesis 1.10. Oh, well, I better put what it is so you'll see that I'm not making it up. I better do what I wrote. 0.05 times 2 years, and I get $10. All right. So we can see that no matter how many years, we're only adding $5 to the account. All right. Well, now let's do compounding. On our first year, and we're doing annual, we know that it's P parenthesis 1 plus R over M raised to the MT. All right. So A equals, now we take the same $100, and we're doing year 1. So it's going to be 0.05 for that 1 year. And this one comes out the same because it's just 1 year and it's done annually. You get more interest the more partitions interest earned for the year. And I get the same. So we're the same. But look what happens on the second year. And MT is 1 time a year for 2 years. So now what I have is, I should have done it for a bigger number, but it doesn't matter. 105.06 cents. Well, um, I didn't get what I wanted. Oh, sorry about that. Oh, I did it wrong. I'm saying, what did I do wrong? It's not this, because N is still 1. T is a time. Sorry, sorry. Say, well, I'm supposed to get more money than that. And that would be terrible there. If it's semi-annual, that would have been what I got in the first year. All right, here we go. 100 parenthesis 1 plus 0.05 close parenthesis up to the 2 years. And I get 110.5. Now, notice I had 110 here, and I have 25 cents more here. Now, it doesn't sound like a big amount, but what it is 2, and what the actual rate is. And that's what we're going to be talking about. The fact that compounding gives you more earnings. So I used 100. I should have used 1,000 and it would have been a little more effective. Well, what we're talking about is the effective rate of compound interest. And that is how much interest made per year. Right. So here we go. It is effective rate. That's effective rate equals 1 plus rate as a decimal divided by number of payments per year raised to the number of payments per year minus 1. All right, so here we go. This is what we do to find it. Now remember that our M is annual for 1, which is what I did. Semi-annual is 2. Quarterly, the most popular, is 4. Monthly, 12. All right. And daily is 360, but we're not going to go there. Okay. So we want to state how much the effective interest yield is for the following. 9% quarterly. So my M is 4 for quarterly, and my R is 9%, which changes to very good interest rate. So here we go. R of E equals, remember what we have, 1 plus decimal 0.09 divided by 4 raised to the 4 minus 1. This is strictly calculator, and I'm going to go 1 plus 0.09 divided by 4, close parentheses, up caret 4, and enter. So, oh, and minus 1. Sorry about that. So our yield, our effective yield is 0.09308, blah, blah, blah. So we want to go 3 decimal places and change it to a percent. So we're earning 9.3% per year, approximate. All right. Did we get that? All right. So let's look at this one. Becky Anderson bought a television set with money borrowed from a bank at 7% interest, compounded semi-annually. M is 2. What effective yield did she pay? How much is she paying? Right, so our rate effective is going to be 1 plus 0.07 divided by 2 raised to the 2 minus that 1. All right, parenthesis, 1 plus 0.07 divided by 2, close parenthesis, up caret 2, side arrow minus 1. All right, and we have 0.07125. So we could make it a percent for 3 decimals of 7.1%. That's not a bad deal. She's paying a little bit more than 7%. Now, this is something that we did in 10.5 and 10.4, figuring out time of investment. Find the present value, which is our A, or future value, following the future amount. Okay, so we want the P, present value. If the future value is 400,000 at 11% compounded semi-annual for 15 years. So let's look at what we have. Our A is 400,000. Our R is 11%, and decimal it is 0.11. Our M is 2 for semi-annual, and our T is 15 years. All right, so here we go. Well, it's a review, kind of, because we've done these. And I didn't show the program, so we're going to do the work. Here I go. A equals P parenthesis 1 plus R over M raised to the M. T. All right, so I'm going to have 400,000, like a 9, doesn't it? Some P, parenthesis, 1 plus decimal 1 divided by 2 raised to the 2 times 15. I'm going to clean it up. So I'm going to have 400,000 equals, and half of that guy is 0.055. 0.11 divided by 2 is 0.055. Okay. Raised to the 30. So I can do the math. And now what I'm going to do is divide by that. So I'm going to divide by this exponential. And I get what my P is. All right. So I get the 400,000. I'm going to divide by 1.055 raised to the 30. So he has at least $80,257.61 deposited in order to get to that value. If we rounded, we would have said he needed to deposit $80,258 to ensure he gets that 400,000 at the end of that. All right. Now we have continuous compounding. We also did one of these in the previous, so we want to definitely get a handle on the formula. Must have a little card with all these formulas to help you. A equals PE raised to the RT, rate times time. So find the present value of the deposit. So this means they're giving us 28,000 at 7.6% compounded continuous for 7 years. So the present value of the deposit. So our A is that $28,000. And our interest, our rate, is 0.076. E is continuous and 7. All right. RT. So we're going to set it up. 28,000 raised to the 0.076 times 7. All right, so I'm going to clean it up so I can look at doing this easier. And I'm going to do this part right there, 0.076 times 7. All right. Okay. So I have 28,000 PE raised to the 0.532. All right. Now I'm going to divide both sides by this E. Right. Now I'm going to stick this in the calculator. There we go. 1,000 divided by, excuse me, second ln, get the E, 532, and enter. Get this, 16448 and 1 cent equals the P. And that is our answer for that question. All right, now we are done with chapter 10. Look at all your notes. Get ready to take that exam for that unit. Thank you so much for listening.